In this video, I want to talk about heat, and in particular our three major modes of heat transfer. That is conduction, convection, and radiation. So to recap a bit of vocabulary, because we haven't had to use this much, so our thermal energy is the energy of the microscopic motion of our atoms and molecules. So, increasing the thermal energy increases how fast these are moving around. That's increasing the kinetic energy of each of them. Our heat is the natural or spontaneous flow of energy, meaning we don't have to do anything to bring about it other than bring two systems close enough together. Spontaneous flow of energy from hot to cold, or from higher temperatures to lower temperatures that we see all the time. So I just want to do a quick correct and incorrect statement. So it would be correct to say something like, this mug of coffee cooled off because it lost 3 kilojoules of heat to the room. So that is, the cup of coffee transferred 3 kilojoules of energy from itself to the room because the room is colder, and that amount that was transferred is this amount of heat. It would be incorrect to say something like, this mug has 10 kilojoules of heat, because heat is this flow of energy. It is a transfer of energy. It is not something possessed. And so, maybe if somebody said that, what they really meant was, this cup of coffee has 10 kilojoules of thermal energy, and then some of that could be transferred by heat to some other object. Anyway, so that's just a little distinction. So when we're talking about heat, we are always talking about energy moving between two systems. Or within, from one part of the system to another, I suppose, is also allowed, but movement of energy. Okay, so let's talk about conduction. So conduction is the flow of heat through an object that is carried by the atoms that make up that object. So if we are to draw a very, very simple model of a material, like a bunch of atoms connected by a bunch of springs. So this is our little masses and springs. So this is, this could be the irons that are making up, or excuse me, the atoms that are making up a piece of iron or something like that. So if we heat up this end, so here we'll make a little cartoon fire underneath this molecule. So we give this one more thermal energy. It's going to start jiggling back and forth an extra lot. That moving back and forth is going to push and pull on its neighbor, which in turn is going to wiggle back and forth a little bit more than it was a little while ago. And that in turn is going to move this one back and forth more than it was a little while ago, and so on down the line. Eventually, some of this energy, by pushing and pulling on neighbors, is going to make it all the way to this other end. So this energy, this is conduction. This heat is spreading because of these atoms in contact with one another. They are, bumping into each other, pushing and pulling on one another. So that is our conduction. So so that's our cartoon picture. Our more schematic picture of conduction might look something like this. We have some bar of some material. We'll just say this is like a rectangular bar of some stuff. This could be metal, this could be plastic, this could be whatever. And this end is at some temperature. So we'll say this is at some high temperature. This end is at some low temperature. So maybe this end we have pressed up against a hot stove, and this end we have exposed to the air or pressed up against ice or something like that. So we're going to get heat flowing through this from hot to cold. So our heat, our variable we use for heat is Q, And so the rate of heat flow, delta Q over delta T, is equal to the following. So it is related to the geometry of this. So A is the cross-sectional area. So if we like slice, perpendicular to this flow of heat, we get some area A. That's what that is. Delta T is the heat difference between these, right? T high minus T low. L is the length. That's very straightforward. So the longer it is, the bigger the length. And K is a variable called the thermal conductivity. So this is a property of the material. That is, some materials are very, very good at conducting heat. So for a particular size object and a particular temperature difference, a large amount of heat will flow. This would be things like diamond or copper or sapphire and I don't know. Yeah, anyway. So those are things with high thermal conductivities. There are also things with low thermal conductivities like styrofoam or wool towels or something. So they do not conduct much heat for a particular temperature difference. And then things like glass and some metal alloys have values that are kind of in between these two things. Okay, so this thermal conductivity is like our thermal expansion coefficients. This is something that you might look up in a table or be given in a problem. But in general, for a piece of copper or styrofoam or whatever, you can look up the number to use for K. Everything else is going to depend on your particular problem. Okay, so we have bigger heat flow, larger heat flows with high thermal conductivities, big areas, and big changes in temperature. A big length, a big size of our object is going to give us a smaller thermal conductivity because this is in the denominator. So if we imagine taking this and smushing it like that, so our high temperature and our low temperature are like this. They're close together, and so we have a big area and a small length. Big area and small length is going to give us a big heat flow. It turns out this is pretty much what a window looks like. So a piece of glass which has a medium value of thermal conductivity, but it is so thin, a single piece of glass is so thin and so big that you can have a large amount of heat flowing through it. This is why windows, single pane windows in your house will get condensation on them. They'll have water condensing on the inside of your windows because the window itself, the glass, is so much colder than the inside of the house because so much heat is flowing out through it. Anyway, so there are lots of interesting things we can apply this question to, or this equation to, but that's just what I wanted to poke at with this. All right, let's talk about convection. So convection is kind of like conduction in that we have some stuff that our heat is flowing into. What's different is for conduction, we're talking about like a steel bar or a piece of styrofoam or whatever that's not moving. It is static. It is staying still. The heat flows through it, but the thing doesn't move. With convection, let me draw the following examples. Let's say we have a cup of coffee that is hot and we have some air that is cold. Okay, so if we imagine some little piece of cold air that is against our hot coffee mug, we are going to have some heat flow into this by conduction. Air is not a very good conductor of heat. It's actually a rather poor thermal conductor, but some heat is going to flow into this. So we're going to heat up this little piece of air. So this piece is going to go from cold to warm, but we still have cold air up here. Okay, so you can show with the ideal gas law that at a particular pressure, like in the room, this warm air is going to be less dense than the cold air. And as we know from our buoyant force stuff, that means this warm air is going to rise. So this air is going to want to move up. When it does that, this spot is going to be replaced by air nearby that is colder. So because of this heating, this like buoyancy effect, you end up with these currents of air moving around your object that's, in this case, hotter. You can also have convection around colder objects doing the opposite sort of thing. And you can end up with these circulating currents where, you know, the air right here is heating up and then immediately moving away to be replaced by more cold air. So as a result of this, you can have much more heat flowing out of your hot cup of coffee than you would if this air was forced to stand still. We know this because if we force the air to stand still, like by putting something around this that is mostly air, for example, styrofoam or fiberglass insulation, you can reduce the amount of heat flowing out significantly. So most kinds of insulation that we think of, like in the walls of our house, we have fiberglass, or in your fridge, it might be lined with big, thick styrofoam pieces or something like that if you tear into the walls. All that is to prevent convection by making it really hard for the air to move around. So if you block the air, if you put all this stuff in the way that doesn't conduct heat very much but blocks the air from moving, it has the effect of stopping this convection, and then you're left with only conduction, which air is a poor conductor, so the heat can't get through it very much. Anyway, so convection is fun. It turns out to be very complicated and depends on lots of things like how much the surface is curved and what the surface is made of and stuff like that. So in general, if you want to understand convection, you should get a textbook on heat transfer, engineering textbook on heat transfer, and they will have more than you need to know about convection for sure. Before we move on, convection is super important because it is responsible for much of the air movement in our atmosphere. So convective cells and things like that. So anyway, convection is very important in climate and weather systems. Oh, and in the ocean, also important under the ocean. All right. The last type of heat we will talk about is radiation. So this sounds scary, but actually, the radiation we're talking about here is black body radiation, also just known as thermal radiation. So whenever you have an object at some temperature, it is emitting electromagnetic radiation. Now, electromagnetic radiation can mean lots of different things. It can mean radio waves, it can mean light, it can mean X-rays, it can mean a combination of all of the above. Radiation here just means, stuff like light that includes radio waves and stuff that is not exactly light that we can see. Anyway, so I said any object at any temperature will emit black body radiation. This is true, and that sounds like it applies to everything, and it does. Most of what we encounter emitting black body radiation we cannot see. So objects at room temperature do emit black body radiation, but they emit it at, as if you take 107, you'll learn more about electromagnetic waves, but they emit it at wavelengths that are much, much, much too long for us to see. So in the far infrared part of the spectrum. If you get objects hot enough, this black body radiation can move into the visible spectrum, and that is when you have an object glowing red hot, or even more extreme, glowing yellow hot or orange hot or whatever, white hot. That means that the black body radiation it's emitting is is now into the visible part of the spectrum, which takes more energy to happen. And so you have to be at a higher temperature to get there. Anyway, so our equation for our radiation is this. dq dt, the rate that our heat flows at, is equal to E sigma a t to the fourth. Okay, so going through this, E is the emissivity, which is a property of the surface. So this has to do with how shiny or how dark, not shiny, a surface is. But emissivity values are generally going to be between 0 and 1, with 1 being a something that's perfectly black, absorbs all the light that shines on it, and something that's 0 is something that's perfectly shiny. Sigma here is called the Stefan-Boltzmann constant, and it is equal to 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. A is the surface area of our object, and T is, of course, our temperature in Kelvin. So, if you just want to estimate these values, you can say the emissivity is about 1. The Stefan-Boltzmann constant is always 5.67 times 10 to the minus 8th, and you end up with A t to the fourth. So the area of an object, if it's a sphere, that's easy to calculate. If it's a cube, that's easy to calculate. If it's anything else, you can wave your hands and say, well, that's pretty close to a sphere. But t to the fourth is where this really gets kind of crazy. So if you have something at room temperature at 300 Kelvin, and it's emitting some black body radiation that we can't see or feel, but we can detect if we have the right instruments. If you increase its temperature, if you double its temperature in Kelvin, so you increase it from room temperature 300 Kelvin to 600 Kelvin, which is roughly 300 C. At 300 C. So that's increasing our temperature by a factor of 2. So that's increasing our power by a factor of 2 to the fourth, which is 16. So if you increase the temperature by 300 degrees, you increase the amount of power coming out by a factor of 16. So anyway, the reason I say this is this t to the fourth, this is a big power. We don't run into powers that big in this class, and in physics it's not super common. So what this means is that at higher temperatures, t to the fourth is going to get really, really big. And so for objects that are really hot, their radiation becomes much more important than conduction, or even, in many cases, even convection. Because, if T is several thousand Kelvin or something, several thousand to the fourth is going to get, it's going to get very, very big. Anyway, so radiation, the unique thing about radiation also is that this does not require any other stuff to be near your object. So conduction requires, a solid thing touching your hot object or whatever. Convection requires some fluid that can circulate near your object. Radiation does not need any of that. Radiation can happen in the vacuum of space. So if you have, a glowing object so hot, but there's no air nearby it to transfer heat to, it is still going to lose heat to the environment by this radiation. And of course, this is what the sun does, right? The sun is really hot, but there's no stuff, or not very much stuff, between us and it. However, this radiation is still getting from the sun to us, heating up the Earth, because this radiation is able to travel through the vacuum of space. Anyway, you can spend years studying conduction, radiation, and especially convection. But hopefully, this is a fun look at some of the ways we can have heat moving around.